Welcome everyone. For our first prep video for the semester here, we're going to look at a few examples of learning outcome I3 where we see how to use substitution rule to help us calculate some indefinite integrals. All right, so hopefully this is review. You've seen this before back in Calc 1. Let's just quickly go over the formula here. Substitution rule is not really one of those formula type things. You think of it more as a process. So the idea behind substitution rule is we're going to have a kind of a complicated monster of an integral here, which has all these x terms in it. And the idea is we're going to do a change of variables in a way. We're going to kind of swallow up some of those x terms, and we're just going to call them u. And it's going to produce an easier integral. That's going to be one of our more basic integrals. So the idea is we're going to let u equal the inner function. So again, a lot of the integration techniques and rules that we're going to be learning are undoing a derivative rule. So substitution rule is undoing the chain rule. So we had, going back to Calc 1, we saw chain rule told us how to differentiate functions when there's an outer function and then an inner function. So the way we choose u is we're going to be looking for the inner function. So look for a parentheses, essentially. And then once we have our choice for u, we're going to calculate du. And this is going to be our new differential. So the way we calculate our new differential is we differentiate the function. So calculate the derivative of whatever we have. So we'll just call it g prime for now. And then we multiply by dx. And so that new differential gets swapped out with du. And the inner function, g of x, gets changed to now just this simple variable u. So we're going from this complicated x term, this x integral, to a hopefully easier u integral. And then we kind of keep going with the integration. So when we're doing this, it's important to remember all of the x terms that we have here eventually have to get replaced with u terms. So there's really no way around it. We got to get rid of all the x's here, and in some way they have to either get replaced with u or du. So let's try an example to see how this process works. We're going to start off kind of easy, and then we'll work our way up. So we gotta dust off some of the cobwebs here. All right, so we've got this integral. 3x plus 4 raised to the power 10 times 3 dx. And our first step for substitution rule is to look for the inner function. So we got to choose u. That's our first step. First step is to choose u and calculate du. All right. So again, our main strategy, how do we pick u? This is not always going to be an easy thing, but what we're looking for is we're looking for parentheses usually. And our choice for u then is the stuff that's inside those parentheses. So for this one, my first choice for u would be the 3x plus 4. So then once we've chosen u, then we're going to calculate what our new differential is. So we calculate du. And the way we calculate this is we differentiate the 3x plus 4. So in this case, we get 3. And then we multiply by our differential dx. And when you do this, when you calculate this new differential, forget about the integral for a second. Forget about all that. Pretend you don't see it. And what we're doing is we're just calculating the derivative of that 3x plus 4 and then multiplying by dx. And for our first example here, we see that the 3dx, the leftover terms in our integral, matches up perfectly with what we just calculated for our differential. So normally, this stuff is not going to be a perfect match. All right, so that's the first step. Choose u, calculate du. Then the second step, well, kind of why it gets its name, is we're going to substitute all these pieces in. So we're going to substitute in our u terms. All right, so what's going to happen? Well, in this case, the leftover term here, the 3dx, matched up perfectly with what we just calculated. So we don't have to do anything special there. We will see later on, sometimes, the differentials are really where it's at. All right, so we're going to fill that in for the 3dx. We're going to replace that with du. And then the 3x plus 4, we're going to change that to this new variable, u. So let's do it. Let's substitute it in. And this is going to give us a new integral, a u integral. So that 3x plus 4 all gets swallowed up and becomes u. So we're going to have u raised to the power 10. And then that 3dx at the end gets swallowed up and becomes just this new differential du. So this way, what we're kind of doing is we're kind of integrating just the outer function. We're undoing the derivative of the outer function, essentially. All right, so now we've substituted all the pieces in. And at this point, you want to check, are there any kind of sneaky x's hidden around? Nope, everything is u now. So now we're ready for the next step, which is step 3, is to actually do the antiderivative. So we calculate our u integral. So we're going to do our u antiderivative here. All right, so the function is just a simple power function, so we get to use our power rule. So if we remember how power rule works, we write down our variable, we add 1 to the exponent, so we're going from 10 up to 11. We take that new exponent, flip it, put the reciprocal in front, so we have a 1 over 11 in front. And then we don't want to forget it, this is an indefinite integral, so plus c at the end. And then we're almost there. So our last step is to then get back to x. So our last step, step 4, is plug x back in. All right, so not 1 over 10. It's going to be 1 over 11. And instead of that u, we want to go back. So we'll put our parentheses 3x plus 4 there. Our original choice for u. So we're just plugging that back in. So we had a u up in our antiderivative here, and then I'm just kind of filling that piece back in. And there we go. We've got our antiderivative now in terms of x. So that's the idea. So, u substitution is going to be one of our standard integration techniques. We're going to use this one probably the most out of all the different techniques we're going to see. So the question is, how do you choose u? And again, you're always looking for the inner function. So if you see parentheses with some stuff raised to a power n, well, you're going to let u equal the stuff that's inside the parentheses. If you see a fraction and there's no exponent on the fraction, it's just some stuff in the denominator, well, then you're going to let u equal the stuff that's in the denominator. And the reason why you would do that is because 1 over u is one of our basic antiderivatives. And then if you see one of our special named functions, like e or sine or cosine, so if you have e raised to some stuff, in this case, e raised to a power, and it's a bunch of x terms up there, well, you're going to let u equal the stuff that's in the exponent. So let's try one more. Let's look at example 2. All right, so let's go through the steps again. Step 1, we have this, we kind of take in our integral. So we're looking at 2x times e to the x squared. And our first step is we want to choose u. So again, well, probably even before we start thinking substitution rule, you want to look at this integral and think, is this something I can just do? So if this was just the integral of, say, like 2e to the x, that's just a basic integral. We don't have to do substitution rule. But because the exponent is more complicated, it's gonna take some heavy lifting here. So what should our choice be? Well, when you're doing this, you kind of want to look at the different pieces of your function. And another strategy for how to pick u is you want to look for the more complicated piece. So when I look at this function, we've got the 2x. It's not too bad. And then we've got this e to the x squared. So in my opinion, the more complicated of the pieces here is that exponential term. So the exponential term is the kind of the more complicated piece of this function. And so when we pick u, we want to look to that complicated piece. So in this case, we're going to let u equal the stuff that's in the exponent. And then once we choose u, we calculate du. So the derivative of x squared is 2x, and then we multiply by dx. Okay. So we're going to start to substitute things in. And one thing that can be helpful, you don't absolutely have to do this step, but once you identify that complicated piece, I kind of like to move that first, put that first in the integral. So I just like to rearrange terms sometimes. So we'll write that as e to the x squared, and then I'll take these kind of easier, these leftover pieces, and I'm just going to move them next to the dx there. So because this is multiplication in between these two things, you know, we can move multiplication around. All right. So now the x squared is going to become u. And we see that our differential, the 2x times dx, well, that matches up, again, perfect with what we calculated for du. So we're starting off easy here. So now we're ready to substitute things in. And this is going to be our second step. We're going to get our u integral. So that u term, we're going to fill that in there. And then we're going to fill in our differential as well. So we're substituting it all. So in this case, we end up with the integral of e raised to the u times du. So again, the x squared became just u. And then the 2x dx got swallowed up and became just our new differential du. All right, so now we have our u integral. So now the next step is to get our u antiderivative. And e to the u is just one of our basic antiderivatives. Antiderivative of e to the u is just going to be e to the u. And we're doing an indefinite integral, so plus c. And then our last step, once we have our u antiderivative, is to plug back in for x. So instead of that u up there, we're going to fill that back in with an x squared. So that's our last step. So last step is to get the x antiderivative. The second step was to get the u integral. And the third step was to get the u antiderivative. So, you know, these steps, these are basically what we're looking for when we grade your solutions. So I want to see this work. I want to see that you're getting a u integral. Then I want to see that you're getting a u antiderivative. And then ultimately getting the x antiderivative. So I know, you know, thinking back to last semester, one of the things especially for easy ones like this, is there's a tendency to maybe skip one of these steps, but make sure you're showing all your work. All right, so we're going to keep going with our substitution rule in class. So we'll see you then. Bye-bye.